Good morning, students. Continuation of the previous topic, system of particles and rotational motion. In that we are discussing moment of inertia. It is one of the physical property of the rotating objects. It is also called as rotational inertia. Inertia word we already got it before, even in the laws of motion also. Mass is measure of inertia. Two different names for the same physical quantity. Both have the same units, kgs in SI system. And more mass, more is the inertia, more difficult to change the position of the object. To change the position of the object or to change the position state of rest, you need to apply some external force. And more mass if you have taken, more will be the force required to change the state. That means mass is the inertial property which opposes or which resists the change of state. The state can be rest state, or if it is already in motion, if you want to change the velocity direction, velocity value, then also you require external force. So that is called the state of motion. Motion means what related to velocity or direction. If it is moving particular direction, again if you want to change the direction also, we require this external force. And more external force is required when more mass is there to change the state of rest or velocity or direction. So this inertial property or inertial property of the translatory motion, we use a term called as a mass. But for the rotating objects, if you have taken, the fan is there, fan already at rest. If you want to rotate it, that opposing that nature of the rotation speed changing. Initially 0 means it try to be at rest, or if it already rotating, it try to rotate with the same speed. Then that property of the material which opposes the change of rotating property, that means the changes in the rotational speed or axis of rotation or direction of rotation. It is a property of rotating object due to which it resists. It resists the changes in rotational speed or axis of rotation or direction of rotation. That property itself is called as a moment of inertia. It is the inertial property of the rotating objects. For the translatory motion, that inertial property is mass, which resists the changes in the speed, direction and rest positions. Whereas for rotating objects, if you want to stop the fan, rotating fan, means already it is rotating some speed. If you switch on the power supply, it continues to rotate with the same speed. If there is no friction, it will never stop, but continuous rotation is coming to rest because of some external torque acting. For this case of the translatory motion, we talk about the external force. For rotating objects, we talk about the external torque. You have taken one rod, fixed like this, about this axis suspended. If you want to rotate it, you apply some force here. When you apply the force, it starts rotating with some angular velocity omega. Force into this is perpendicular distance is nothing but equal to torque will be there. So torque is external torque, produces rotation motion in this object. When it is at rest, it increases the speed from 0 onwards. So omega changed, but already rotating. If you want to change the angular velocity omega, again what is required is torque is required. You want to decrease the omega or increase the omega, what is required is the torque, and the torque which is supposed to be external torque only. And if the moment of inertia, we are going to discuss the formula for this. Moment of inertia of this object, it depends on the mass and distance of the mass from the axis of rotation. If the moment of inertia is more, it is more difficult to rotate the object. If it is already rotating, it will be more difficult to stop. Same rod, if I have taken some small length or small mass, this is a large mass, here I have taken a small mass. Less mass, less moment of inertia, and less moment of inertia, easy to stop and also easy to rotate from the starting objects. Is from the starting point to rotation, or if you change the omega, if moment of inertia is less, it is easy to rotate the body or change the speed of rotations. So here, if, better take it as extra point, if moment of inertia, the symbol for moment of inertia is I, or sometimes we use a symbol only small letter m dot I also we can use. Moment of inertia, mi will take. If moment of inertia is large, then it is difficult, it is more difficult to change the rotational speed, means angular velocity, comma direction of rotation or axis of rotation, we can say. What is required to change the direction is torque. External torque is required. External torque is required to change the state of rotation of objects. If moment of inertia is less, it is easy to start the object from rest, and it is easy to stop the object if it is already in rotation. Moment of inertia provides the stability to the object. Third point, moment of inertia, m dot I stands for moment of inertia, provides stability to rotating or spinning, we can say, object. That's why top, which is spinning, can stand on the tip only while spinning. With angular velocity it is spinning, then it can stand on the tip. If it is not spinning, it falls. So this moment of inertia comes into picture. Main important is when it is rotating, it comes into picture, and which provides the stability to the object. Okay, as we said, the rotating objects are more stable than the stationary objects. The property is moment of inertia. Moment of inertia, which is, this is I, is proportional to mass and square of the radius. It is independent of the omega actually. That is where point is important. Moment of inertia do not depend on the omega, but comes into picture when there is omega. Omega is related to the rotatory motion only. Angular speed of rotatory motion. When the top is rotating, it is stable, able to stand on the tip. While not rotating, it is falling out. That property is due to moment of inertia. Tops, different types are the light, weight, heavy ones. Okay, depending on the more mass, more moment of inertia, more stability for the top, can rotate for longer timings. It is coming to rest only because of the friction. If you take the same top in the space and if you rotate it, no, it won't stop. It will continuously rotates. And more R is the distance from the axis of rotation. That means it more heavy, and mass, resultant mass at the more distance from the axis of rotation, the more is the moment of inertia. Similarly, cycle wheels. Cycle wheels, the mass is located at the tips, end points, and thin spokes are used. Why thin spokes are used for the cycle wheel is, the cycle wheel, you might have seen it. More mass is located here. This is the axis of rotation about which the wheel rotates. This is got a little rust, old wheel, cycle wheel, and also has some wobbling motion. And thin spokes provide less mass. So total the heavy mass is at this point only. The distance from the axis of rotation mass is more, and more distance from the mass means more moment of inertia, more stability for the wheels. When you are standing on the cycle, when not in motion, you cannot stand on the two wheels. It will fall either that side or this side. But it is able to come into rest and stable, not rest, sorry, it is stable while moving. When it is moving, the wheels are rotating. When they are rotating, wheels, moment of inertia makes it stable. So cycle comes to stable when it in motion. Even if you push it to the sideways or turning at the turnings, bending to the sides, cycle won't fall because of the property of the moment of inertia of the wheels. And why, that question they will ask you, why thin spokes are used, why not thick spokes, why not solid wheel completely, is because moment of inertia increased and stability of the wheels increases when the moment of inertia is more, which is depends on the distance of the mass from the axis of rotation. So thin spokes are used so that the mass is located at the end points. We can say, simply say that to increase the moment of inertia, mass is at the rim. This end point is called as a rim, or rim borders, and thin spokes provide the less mass in between. So mass is only at the ends. So more mass at the rim, more is the moment of inertia. I repeat once again, why thin spokes are preferred to thick rods or solid wheel for the cycle wheels or motorcycle wheels is to increase the moment of inertia. Mass should be at the rim only. For that purpose, thin spokes are used. If thick spokes are used, thick spokes means their mass also need to be considered, then the resultant mass will not be at this point. The resultant mass will be in between from center to the tip comes. Solid wheel, if you take the solid wheel also, center of mass will be not at here. Mass is located everywhere. The resultant mass will be at some distance from center to here, but not more distance will be getting it. That effective distance called as the radius, effective radius of gyration. That point is not, later we discuss, whatever. To increase the moment of inertia, thin spokes are used. Next, similarly, bullock cart wheels, if you check up, the bullock cart wheels also located, have the large radius and more mass located at the end points. What is the advantage of this is to increase the moment of inertia. And why it is coming to rotation is when the wheel is moving forward direction, it is pulled forward direction by the bulls. Then the bottom is also trying to go translatory motion, but the friction force opposes this. If it is trying to go forward, if it is trying to slide forward direction, the molecules are going trying to go forward. The frictional force opposes that. Frictional force opposing this object sliding forward direction, friction force opposed to motion. The friction is providing the torque for us. Torque is nothing but equal to force into radius, means distance from the axis of rotation. So friction force acts tangent to the path at this point, perpendicular to the radius. So torque equal to Rf. More radius, more friction, more torque. More easily you can rotate the wheels. To provide the more easy rotation for the wheels, bigger wheels if you have taken, more radius is there, more torque is there. But cars are provided with the smaller wheels because they are designed to travel with high speed. High speed, but torque, however, depends on the same relationship. Even then, for the stability on the roads, to more height from the ground means more unstable at the turning points due to the centrifugal force, which is that pseudo force makes it to skid or overturns. To avoid that, we take the smaller wheels for the cycle wheels. For bullock carts are not designed for the high speed. Even trucks are not designed for the high speed, so their wheels are bigger in size. And race car wheels are very smaller to the ground also. That is because of the stability purposes, not because of this moment of inertia. But they are made heavy. Thickness is independent of the friction, but more heavy if you have taken more mass, more moment of inertia, that also provides stability for the wheels. Next is bullet fired. Bullet coming from the guns and even the pistols, even in the air gun also you can check up that lead pellet coming out. Inside you will find the grooves. Grooves are there on inside the barrel surface. You will find the grooves, spiral grooves. So when the bullet is coming out, it comes out due to the friction. It comes out with the spinning out. Whenever it is spinning is there, the bullet gets the stability. The spinning bullet has a more stable than non-spinning bullet while going fired. If any wind comes, the wind can disturb that non-spinning bullet to the sideways, but not a spinning bullet. Similarly, the satellites, around this earth, orbiting satellites are there. These satellites are provided the spin. The satellites are provided the spin to provide the stability. Otherwise, any particles coming from the space, they hit it, debris, means other satellites parts, or even the meteoroids pieces, stone pieces coming from the space. If they hit it, it may change the position. But if it has a spinning pose, it is already having the spin, it is stable. It won't be getting disturbed that easily unless very heavy piece falls on it. So moment of inertia gives the stability for the rotating object. And the pendulums, when you are doing the experiment with the pendulums, one of the precautions you have to take is that bob should not spin. Bob should not spin. While making it oscillate, many precautions you need to take. One is the distance of the movement or the angle by which the pendulum taken to the sideways should be less than 5 degrees, and so that the path is a straight line path. For the simple harmonic motion condition, the bob should move a straight line path, means you have to deviate by the small angle of oscillations. Another thing is that the bob should be very small to avoid the air resistance. Another thing is that the bob should not spin. If it spins, as it oscillates, it should oscillate in a single plane. But if it spins, what happens is, if it spins, that spinning motion opposes the other kind of motions. It will try to spin in the same plane, so it will not try to go oscillate. So it comes to rest very quickly. Damping takes place very quickly if this bob is spinning. So you should not take the bob spinning while doing the experiment with the pendulum, simple pendulums. Many applications are there for this moment of inertia. Next, derivation is there for moment of inertia. The derivation is for 3 marks question. And one more thing is that even if we are in the mob or very highly populated areas, the stampede is a problem. In that such cases, any disturbance comes, many people are there. If you have to pass through the people, if you walk straight, it is difficult. But if you rotate and move forward direction, easily you can move forward direction, because if you are rotating, you will be stable. Anybody comes in the front of you, will be pushed to the sideways. Expression for moment of inertia. Expression for moment of inertia, I. Consider a rigid body of mass m rotating in circular path of radius r with the speed v. Then translation kinetic energy at an instant. Translatory kinetic energy Ke equal to half mv square, but v equal to omega r. What is omega? Is angular velocity or angular speed? Angular speed of rotation. V equal to omega r is a relation between the v and omega. Substitute that formula. If you take v only, it is called the translatory kinetic energy, but it is rotating. But at the instant, velocity is along the tangent. At that point only, we need to consider this kinetic energy. It is kinetic energy is always a scalar because the energy place. So v is supposed to be mapped to the velocity we need to take. Next is the speed. V is also can be taken as equals to omega r. Omega is the angular speed. If we mention omega, then it becomes equal to rotational kinetic energy. Rotational kinetic energy. This is called the translational. Rotational kinetic energy. Kinetic energy rotational is equals to half m into v square becomes equal to omega square r square. But what is constant for the all points? This is a body. It is not a point object, but it is not a particle. We are considering the rigid body. It's not a particle. Please, particle means only single point we need to consider. But we are considering the object means it has some different points. So each point is at different locations maybe. The resultant mass we are taking as the center of mass, we can consider distance equal to r. So we got the rotational kinetic energy expression, this one. But for different particles of the object, if you have taken for n particles of this rigid body, located at the different points, what you can get is for n particles of rigid body of masses m1, m2 and so on mn located at distances r1, r2 and so on rn from axis of rotation. So we can write this total kinetic energy becomes equal to, this is the total rotational kinetic energy. Kinetic energy rotational is equals to half into mi ri square into omega. What is constant for the rotated rigid body is, this is a body, points, different particles on the same body we are taking it. So for any rigid body in rotation, omega is constant. Omega is equals to, is equals to half omega into sigma mi ri square. I is equals to 1 to n. We are taking the total one, sum of all the kinetic energy you need to consider for the m first particle, second particle and so on. So ith particle, if you take, no, I values are taken from 1 to n particles total one. What is this omega? Angular speed omega is equals to constant, for all points, of rigid body. Angular velocity or angular speed omega is constant for all points of the rigid body. Therefore omega is constant means we may take the remaining term here, and the final expression becomes equal to kinetic energy rotation is equals to half I omega square is the formula, where I equal to sigma mi ri square, I equal to 1 to n is called as moment of inertia. Up to this derivation you need to take for 3 marks question. It is important one. So moment of inertia depends on what factors is I. It depends on the mass. It is actually proportional to mass and square of the distance from the axis of rotation. So moment of inertia do not depend on the other factors, do not depend on the angular speed omega. It depends only on the masses and distribution of the mass about the axis of rotation, which is nothing but distance of the particles from the axis of rotation. And for this actually diagram not required. You can imagine one object of the mass m rotating with the speed v. Okay, distance from the axis of rotation, we can take the different particles r1, r2, r3, etc. You can take even the fan blades. If you take the fan blade or rod, if you have taken rotating, this is a mass m rotating with the speed v, but different particles if you have taken this axis of rotation, this point is m1, m2, m3, same type of metal means mass will be equal. The distance from the axis of rotation r1, other particle distance is r2 and so on we can consider, but diagram not required for this derivation. What is constant for all the particles on the rigid body is omega is constant, same omega will be there. Extra points. Black ink. This will be asked for on what factors the moment of inertia depend. They will ask you for 1 mark or 2 mark questions. Moment of inertia. Mi you can write depends only on mass and distribution of mass Moment of inertia depends only on the mass and distribution of mass from axis of rotation or about axis of rotation. Distribution of mass about axis of rotation. That means distance from the axis we can take. The mass distance from the axis it depends. Next is this moment of inertia do not depend on the speed of rotation, means angular speed. Moment of inertia do not depend on angular velocity or angular speed. Velocity is a vector, speed is its magnitude, omega. Next, this point is important ones. Next is SI unit, and one more thing is it is not a vector, it is not a scalar, it is called as a tensor, but added is like a scalars only. That point we will take later. Next is SI unit of moment of inertia. Moment of inertia is proportional to m into r square. Proportionality constant can be 1, can be different numbers we will get for the different objects depending on the axis of rotation. But finally the proportionality constant is only a number, do not have units and dimensions. So we need to consider only for m and r, kg meter square. Kg into meter square. CG units means grams centimeter square. Next is dimensional formula of moment of inertia is equals to kg means mass, L square, ml square we can take, or t is not there, so t to the power of 0, m L square t 0. Mass, m symbol, length, meter square it is, means distance, length, means dimension symbol is L, ml square. Next is moment of inertia is tensor. In your textbook it is given as a scalar, but it is similar to the scalar metric, but it is not a scalar place. Tensor it is added similar to the scalars, added similar to scalars independent of the angles. Independent of angles. If depending on the angle means that is supposed to be vector. If it is dependent on angle means it is not depending on the vector. So moment of inertia of the two objects if you have taken, if I take the one rod, moment of inertia is I1. I take one more rod, moment of inertia is I2. Different masses, different length maybe. So what I take is I add these two rods, fix it one over the other. Then total moment of inertia becomes equal to I1 plus I2. The angle can be 90 degrees, the angle can be anything you can take. Even if I take like X also. Two, what is I1, other one is I2. Here it is I1, this is I2. So if I take the object, I am rotating object like this is a moment of inertia I1 and this is moment of inertia is I2. For these two I am fixing it, the moment of inertia becomes equal to I1 plus I2. I can keep it perpendicularly, I can keep it like this, I can keep it like this, whatever is the angle between these two lengths, independent of that, just to take moment of inertia is I1 plus I2, similar to the scalar addition we need to consider. If it is a vector, we need to consider the angles, but it is not a vector, it is a scalar quantity. It's similar to scalars, we take the addition, but it is called as a tensors. Tensors of second order it is. Okay, we stop now. And theorems are there for the moment of inertia. Those theorems, each one is for applications 3 marks question is there. We will discuss that in the next class.